to talk today really briefly, since I've had problems, again looking at adders and subtractors. Now remember, I've actually shown this concept before, and that is, yeah, we have an adder. And an adder will have an A and a B input, right? Because we're typically adding two numbers. And if we want to, we can either do addition or subtraction. And how do you do that? Well, you do that by maybe doing some concept associated with, remember, if you have two's complement numbers, what's the difference between addition and subtraction? Okay, what's in regular math, what's the difference between addition and subtraction? Okay, let's go back to 5th grade. A plus B is the same as A minus a minus B. And that's some of the aspects that you can do that, well, if you want to do subtraction, all you have to do is take the 2's complement of B when you bring it in. So let's take a look at an example here. See, for the lab, I didn't have you do subtraction, did I? I had you do only addition. You did that? Okay. So adding negatives is nothing more than just adding, right? And your input of the negative was just switches. You just made sure that you put it correctly in there. And in fact, you notice how easy that was, right? You're just adding a negative number to a positive number. So one of the things you could do is you could take a positive number and then just make it a negative number inside. Now, how would you do that? What is a negative number when you're talking about 2's complement? Okay. First of all, it starts with a 1. That's a good sign. What else? What did we do when we took the complement of a positive number? You inverted every single bit and added 1. So adding 1 would be like what? What's a nice way to add 1? Using a count or using an adder. A carry in. Right? So all you have to do is, and I think we showed this up here, you're just inverting all the bits, right? And then you're adding 1 in the carry in. And that's all it is. So what do we do here? Well, we just determined that B is going to either be passed in, but if you subtract, and so you have this extra bit over here that says subtract, every bit for B is inverted, and then you also add a 1 in here for carry in. That's pretty easy. You can make your own arithmetic logic unit, ALU, and we're going to look at that in a minute. Here's another example how you can do this. I think you've already done this, though. So, there is one problem, and that is, remember, okay, I'm trying to go back, and do you remember overflow, yes or no? All right, so I covered overflow long ago. You know the concept. You have 8 bits. So here's a nice quiz or test question, right? You have 8 bits. What is the range of numbers? If it's 2's complement. Everybody know that? All right, the formula officially is negative 2 to the 7th to positive 2 to the 7th minus 1. So this is associated with how many bits you have, right? Because we have positive and negative numbers. What happens if I have only positive numbers? All right. We're going to go obviously from 0 to the, oops. To the 8th, right? Right? Yeah. No. To the 8th minus 1. Don't forget we started counting at 0. Very important. That will get you a wrong answer in multiple choice, wouldn't it? Seems like you need a little bit more practice. So I'd like you to do the following. If you have a 16-bit number, you could use calculator. If you have 16 bits, give me the unsigned range. And then also give me the 2's complement range. So turn to your neighbor and figure that out. So our answer for this, which you will provide me, is 0, 2, 6, 5, 5, 3, 5, which is also known as 0, 2, 2 to the 16th. Minus 1. 2's complement will be negative 32, 7, 6, 7. 32, 7, 6, 7. All right, everybody got that? So an overflow, if you remember, would be when you have two numbers that go outside of the range. So if I have 2's complements numbers that don't really seem right, well, it'll occur because in this case we have 16-bit number. Let's say we're adding 30,000 plus 20,000. Is that in the range of a 2's complement 16-bit number? No. And we know this because, as we said, when you know you have overflow, when you have a positive number and you add it to a positive number and your result is a negative number, that is an overflow. An overflow is when you have a negative number and you add it to a negative number and you result in a positive number. That is a overflow. Can you ever get an overflow when you add a positive number to a negative number? Can you ever get an overflow? Well, you have to represent it. It has to be representable in 16 bits in the first place. So it can never be 2 things to begin with. So the answer is no. In fact, the answer is never. Because the whole idea is that when you're adding a positive with a positive, you're getting further away from 0. When you're adding a negative to a negative, you're getting further away from 0. When you add a positive to a negative, you get closer to 0, which will be your result. So that's the whole thing. Indicate when an overflow has occurred when you have this situation. So, as I've talked about it, yes, here's the example of overflow. When you have two positive numbers and your result is a negative number. When you add two negative numbers and your result is a positive number, and in this case you're adding a negative and a positive, you'll never have an overflow. By the way, you should be able to figure that out with logic, shouldn't you? Is that yes or no? So how do you think you would figure that out with, oh, that's one way. This is even, it says it's simpler, but it's harder to determine this with logic sometimes. Well, you do get, here you go, here's your circuit. So let's look at this. What will be our truth table for this? All right, assume that we're going to have, what's our input for this? All right, do you have a question? Well, first of all, here it is, right? Well, let's look at the truth table. If our result here is S, right? So we're just looking at the bit of S3. And we want to just worry about A3 and B3. And so our result for overflow will be O, right? If you look at 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. When will we have a problem? Well, if you're adding something that's positive to something's positive and you get a positive number, is that overflow? No. When you're adding something positive to something positive and you get a negative number, is that overflow? Yes. This is the same way. When you add something that's negative to something negative and you get a positive number, is that overflow? So now you're going to be left with this. And actually, if you try and simplify this, it cannot be simplified. Because if we look at the Carnot map, remember back to those old days? I believe that is our Carnot map, right? And there's no way to put these two together. This is another way that will give you an exclusive OR if you do another type of detection. I like the simpler one. All right. I want to go to now look at, this is the crux of the whole semester, is how do you make an arithmetic and logic unit. I've done a brief example of this way earlier, but these are different types of operations you might want to do between A and B. A and B would be your two numbers. So if these are two 8-bit, two complement numbers, although I should say it doesn't necessarily, we're assuming that if they are arithmetic, that they're two's complement. However, there is a possibility that this may be just logical data. Now, why would I have logical data in an arithmetic and logic unit? Here's the question. How many of you are in Engineering 1202 this semester? Raise your hand high. Come on. Let me see it. How many of you took 1202 last semester? All right. What did you do in 1202 in the computer engineering part? You programmed. Is that all you got out of it? Man, I'm in deep doo. All right. right, what did you do? You guys read ports coming in, right? And then you might have done maybe an AND operation between two different numbers. So your data really wasn't 2's complement numbers. It was data that you read in on a port. So your ALU might need to do some operations like addition, subtraction, or maybe just increment by a single value. Or maybe just pass the whole value through. Or maybe you work on it logically with an AND, an OR, an exclusive OR, and a NOT. And these would be bitwise. So you're doing everything bit by bit. So let's say that we're going to have this box, and we're going to call it an ALU. And this is, I've mentioned to you, it's the upside down pair of pants, right? Input is A. Input is B. So these are two different numbers or logical values that you are doing. Your output is going to be S. And then you're going to have control lines that go in that actually say what happens. This will be X, Y, Z. We'll determine if this ALU is going to do an addition, a subtraction, an increment. Adding 1 is an increment. Passing just A through, or doing an AND, an OR, an exclusive OR, or a NOT. And so we're building up to everything. What do you think we need as a part of this ALU? Well, we need those adders. Remember those adders? What else do you think we might need? Something sequential? Like a register. Remember registers? So we might need this register here at the end, based on what our arithmetic logic unit is going to be. So we have our input A, and based on what we have, our little switches over here, we'll determine what our functionality does. You could actually have, like, this could be a separate adder. This could be a separate subtractor. How would we do a subtractor again? You start with an adder and you invert all the bits and you add 1 and the carry in. And then you could use a multiplexer and select which one of these will be saved off. But this is a lot of wires. This is a lot of functionality. It would be nice if we could just make this into one single box. So, a lot of wires there. So maybe we could think about some clever ways to do this. And I've already shown an example earlier. I showed you how we can choose our input to be 1 and only the value of 1. And A, and then you add those two together. So let's take a look at some other stuff we could do when we make our ALU. We could make it more efficient and not just one huge multiplexer all the way at the end by using an adder and doing clever things with that adder. In other words, changing the data that we pass through. So we're going to have what we call an ALU extender. So we can do some additional stuff all the way at the front, and that will give us less wires and a lot more stuff all the way in the end. Notice this C in there. What do you think we're gonna? Oh no, I'm yawning. What do you think we could use a C in for? Add? Really add? Add what? Okay. And what about the other thing we talked about? What about another one of the functionalities we have to do? What do you think we could use C in for that? Increment. So you have this, remember this function over here where you're saying A is A plus 1? what a wonderful way to just add +1 in there. It's just using the CI bit. So there's all sorts of wonderful stuff you can do so that you can, depending on what this AL extender is, for each one of the bits it'll do pretty much the same thing, and you might also have, oh, look at this over here. All the way at the end, you could use this X and Y and Z to actually determine what goes on there. So if at one point I want to add 1, that's when X is 0, Y is 1, Z is 0. Is there any other time you might want to have Cn equal to 1? Oh, this one right here too. So that we're going to have a little bit of logic based on, it looks like, right here. Are they close to each other in the table? Can you put them together? Run on that?
I don't think so. Maybe we could
So here we have this extender. So, by the way, when you see something like this, X, Y, Z, that means that in this block. So it's just one quick and dirty way to actually say X and Y are going to be used by all of these. So let's look at how we can do some of these logical blocks. If Z are all zeros, we just want to pass A to AI. Is that somebody's phone for a text that has the, was that the old? So if X, Y, Z is 0, 0, 0, we just want to pass it, right? If X, Y, Z is 0, 0, 1, we'll want to invert everything along the line. And then all these other things we might want to do some big lines. So let's take a look. So this function calculator, we're just going to do design. And what would be one of these things for function? This might be an interesting thing to study. So what I want you to do is I want you to think about what is the logic. Going to so we're in Vahid, chapter 4, slide. What slide was that? '65 and 66. We're going to have the following. We're going to have an X, a Y, and I'm just going to make life really easy. What will be I, A, and I, B. And if I remember correctly, this one was A plus B. This was A plus 1. This was just simply A. This was and or not A. A? Do we care what IB is? Remember IB? We had our we had A going in and B going in, and this is going to be IA and IB coming out, right? Do we care what IB coming out is? Yes or no? No. So you know what? That's a don't care. What is A naught, right? All right, let's look at all this over here. What is, in this case, with A and B, what do we pass through? We're going to pass A through there. What do we pass through in B? What do we pass through? I already told it what it is. All right. What about this case? IA, what is that going to be? A. What is B going to be? Remember, this is just bit by bit. We're only working about a single bit because this is all we're doing is we're identifying each one of these individual bits. All right. So the output will be B naught. A plus 1. What do you think we're going to have? What's this one? A. What is this one? 0. Because remember, later we're going to use the carry in. We're going to pass 1 in. Okay? What is, in this case, what is it going to be? A. What is this? Remember, what's our end thing? Our end thing is an adder, so whatever is there, it's going to add. So it should be 0. Let's look at this. A and B. What are we going to pass in A? Whatever A and B is, right? We're going to pass here 0. Oh yeah, that would be helpful. 0. A or B. What are we going to have here? A or, that's the or, so keep that in mind. What are we going to pass in B? 0. A exclusive or B. What is it going to be? AX or B. What is B going to be? So, thinking about this again, should this be X or should this be 0? This should be 0 as well. So actually, you look at all this logic, this isn't all that hard, is it? This would be a really, really, really good test question. Or we could just do it in the next class. What do you think? Both. Now, I want you to ruminate on this. And hint, 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 I think you should really ruminate on slides 65 and 66 and what I just did right here for our next class on Thursday, which may have a quiz at the beginning where you might have to maybe solve some of this logic inside. I like this. Question? I have answered that already. Anything else? Thank you very much.